Yesterday we learned that exponential models follow f of x equals a times b to the x. We talked about thinking of this as a transformation, and we were able to get some graphs out without like plotting points. Now the important thing for today is we're going to think of this in terms of fitting data. So what that means is I'm going to give you situations where, for example, I give you population and growth rates, and you should be able to quickly write down an equation that would model it. So the thing to keep in mind here is that b, remember, if b is larger than 1, it's growth. If it's less than 1, it's decay. And so often we write it like 100% plus or minus the rate. And what this means is, for example, if we have a 2% growth rate, we would think of that as 100% plus 2%. Now, if you write that as a decimal, that would be 1.02. And that would be our b. We would have an a and then like an x right here. So today we're going to start off by just writing it as a percent. And then the other thing to keep in mind is this is normally the start amount. So, for example, in Minnesota in 2014, I believe, 2014 we had 5.5 million people. Now we kind of did this example yesterday. We had 5.5 million, and as far as Google can tell us, the growth rate is actually 2.89%. So to really quickly get a model for this, all we have to do is write f of x, and then the start value is going to be 5.5, and that is our a, okay? The growth rate is going to be 100% plus this. So you would think that actually we're going to think of b as like 102.89%. And when we write that down as our b, it's going to be 1.0289 to the x power. So we've really quickly created a model for the population of Minnesota, and we didn't have to do any of plugging in those points. So that's great if we want to do an exponential model. So another example, this might be some old information, but let's do, for example, the population of Earth with 2 E's. Okay, of Earth. Okay, we're going to say that in the year 2000, there was approximately 6 billion people. Okay. Now, we're going to do an exponential model, but we're also going to talk about why we have this other model called the logistic. So, we know that the growth rate of the Earth is about 1.1% growth. Okay, so in our model here, we can write f of x equals, we're going to do this in billions, so I'm just going to write 6, and for a growth rate, it'd be 1.011 to the x power. Now, that will work, assuming that the Earth could just grow forever and ever. This is simply an exponential model, and it's assuming that there's no capacity. Now, on the other side, there's something called a logistic. So a logistic is going to start taking into account that the population cannot grow forever, and so what we need to do a logistic is actually a second point and a carrying capacity. So, for example, if they were asking for a logistic model, they would have to also tell you that 10 billion is an estimated carrying capacity for the world. Also, they might give you another year, 2015, and in 2015 we had 7.3 billion people. Okay, and so one thing I forgot to mention here is this exponential model over here, we assume that the year 2000 was year 0. And so we're going to do a similar thing over here. To continue making the logistic equation, I'm going to use my old point, 2006, and I'm going to call it 06. The second point I have is 2015, which will be 15, 7.3. Now this should be familiar from what we've done already. If you have 2 points, you could fit it to the model by plugging those points in. And the other thing to keep in mind now is we have C. But remember that the logistic is just a little more complicated. It's going to be C all over 1 plus ABX. Okay, so we're going to continue now. The logistic is a lot more work. Exponential, we were done in a second. Logistic, we got to plug in what we know. So already, we know that 10 is going to be on top. And I will say this a million times, this A times BX has no relationship to anything on the graph. You just have to figure out A and B by plugging in your 2 points here and here. Okay, so first of all, we're going to plug 0, 6 in. So 6 is my answer. 10 all over 1 plus A times B to the 0. I've plugged in 0, 6. Alright, we know B to the 0 is 1, and so really, this is just 10 over 1 plus A. Now, I'm going to multiply by 1 plus A on both sides, so I'm going to get 6 times 1 plus A equals 10. I'll do 6 plus 6A equals 10. 6A equals, and 10 minus 6 is 4. So A is going to be 2/3 when we divide by 6. Alright. And now, it's not always going to come out really nicely. I'm actually surprised because this is information, real information about the world I've pulled off Wikipedia, but we have a nice A here. Now let's go back, kind of, to this and plug it back in. Alright, we know that now our model is 1 plus 2/3 b to the x. So when we plugged in that first point, we got the A, and now we have to go and get the B. That's where this second point comes in. So to recap, at this point we've already plugged in C. We plugged in our first point, got A. Now we plug in our second point and get B. So we're going to have 7.3 equals 10 all over 1 plus 2/3 b to the 15th power. Alright, now I'm going to do a maneuver here, a fraction maneuver, where I can actually flip these around. So this would be 1 plus 2/3 b to the 15th equals 10 over 7.3. Now, the reason that works, a quick explanation is if you have 12 divided by 3 equals 4, you could flop these around. 12 divided by 4 is 3. So that's a quick fraction trick. Okay, and then I subtract 1. So we will write that as 2/3 b to the 15th equals, and I mentioned before that we want to kind of avoid getting to decimals as long as we can, so I'm just going to write -1, and when I get an expression at the end where b is alone, I'm going to put everything in the calculator at once. Okay, so to get this 2/3, I'm going to multiply by 3 halves on both sides. So 3 halves, 10 over 7.3 minus 1. And I'm going to have to take the 15th root of all of this. Okay, now I got to put that all in my calculator. Now remember that to do the 15th root, you would actually probably do to the 1/15th power. So remember, like the third root of x is actually the same as x to the 1/3 power. Same thing with 15. Alright, plugging it in the calculator. Alright, I'm getting a b value of 0.961, and we said that 3 decimals would be just fine, so there it is. Now, we have to summarize. Our model is going to be 10 divided by 1 plus 2/3, 0.961 to the x power. Okay, now let's graph these on decimals and take a look at the differences. Okay, so I quickly put all this information in here, and I put in 0.6 here, representing in the year 2000 we had 6 billion people. The first equation looks like this. So here is a n exponential, but you'll notice that this thing, if you zoom out, it's just going to keep growing forever. And we know that the Earth is not going to have a population that explodes that much due to restriction of resources. Okay. Now, if the idea that 10 is our carrying capacity, we should somehow get a model that shows that we are actually going to start leveling off in the future. Okay. But one thing to keep in mind, in the short term, exponential models are pretty accurate. Okay. So that is our exponential model. That's the one that took a second to make. Now, what we want to worry about is we want to worry about this other point from 2015 and a carrying capacity of 10. We did all that algebra and we got this function. When you graph it, you should see it go through both points, and you'll notice that population was growing a lot, and it's actually starting, according to this model, if the carrying capacity is at 10, it's starting to actually level off already. And so we have a graph that would be able to predict in 2050, we're probably going to have about 9 billion people. So if you wanted to, you could actually create a different model, because this right here is an estimate. So there are some people who say, wait a second, 10 billion is not actually the carrying capacity of the world, so let's go with 20. The issue is that you'd have to go back, use these points, and recalculate your A and B. But that's very doable. Okay, so there's one other thing that we will have to look at, and that's decay and half-life. Now, I wasn't very clear on this a little earlier, but we said that B could be 100% plus or minus a rate. Now, when it's like minus a rate, what that means is we're actually going to get a B value that's less than 1. So say that this is like 5%. 100% minus 5% is 95%. Your decimal is going to be 0.95x. And you're going to see a rate of decay kind of like this. So, be aware that when the population is decreasing exponentially, you're going to have a B that is less than 1. Now, a very common example is half-lives of isotopes. And so this is just this is not completely accurate, but it's around the ballpark. The carbon-12 atom has a half-life of about 2,000 years to create a model for the rate of decay. Now that means that it's going to half every 2,000 years. So we're going to still have a starting amount, A, which they didn't give us in this example, so we'll just leave it as A right now. And we will be halving every period because it's a half-life. Now the thing we have to adjust though is that we can't just plop an X up here. We have to think that it's going to be every 2,000 years, which means that our time should be per 2,000 years. And so this is a quick way to make a model for half-life decay. And you know, a lot of times they're going to actually put something here like 10 grams or 20 grams. So this is just how you set it up. If you have a half-life, make sure that when it says every time period, your time period is going to be below your time as a fraction. And this makes sense that if you put 2,000 in here, it's going to turn this into 1 halving.